Namastu ma vidvishavahe. Om Shanti Shanti Shanti. Harihi Om Tat Sat. Today is a special occasion, as you know. There's a tradition in most of the institutes, particularly research institutes, and we also can claim to be a research institute with which teaching is attached, in which when a senior teacher retires, that day we talk physics, particularly about the area in which that teacher has been working. And it's a very small kind of a seminar in which his students present their work, and we have a couple of talks. And the research scholars and the students of the department participate along with the faculty. So at the end of it, everybody, all of you will get a packet of sweets, and we will host lunch for the faculty and wish the retiring teacher well. As you know, Professor Parthasarathi Majumdar is leaving this institute formally after having served here for quite some time. He was earlier in the Saha Institute of Nuclear, as you know. From there he migrated here. And tomorrow is his last working day and attaining superannuation at the age of 65 years. So thankfulness to his services to this institution, we are expressing in the form of a brief seminar, because scientists will be more happy if you talk physics and science rather than have farewell speeches, which most often end with only cliché. So, and it's very embarrassing for the person concerned, and the person who talks also sometimes tries to exaggerate, sometimes not. So we will make it very objective and scientific by having a very short seminar. And I also want to introduce our new talent, Brahmachari here, who is name is Aditya Arvind. Now he's called Brahmachari Aditya, who was doing his engineering physics for 4 years, BTech from IIT Madras. From there he went to the University of Texas at Austin and did his PhD in early universes and cosmology, which gels with the work which Professor Majumdar has been doing for years. And thereafter he went to South Korea for a postdoctoral work. Now he is with us as a brahmachari. As you know, brahmacharis are people who come for a spiritual and monastic life in the Ramakrishna order. And if they are qualified enough to be able to teach and research, we use their services also. So he has not been assigned any formal teaching or research work in the department as yet. So I told him, since you are new, because you have been listening to our teachers all the time, so it's some kind of a new venture. So he also will talk about what's happening in these days in the early universe and cosmology region, very briefly, about 20-25 minutes. Then Professor Majumdar's PhD student, Alok, he is on the way. He was away for some time. He returned in the morning. He has just said, I'm just on the way. He'll be arriving any time. So we'll begin with your presentation first, Aditya.
my voice audible? Yes. Okay. Okay. Yes. So thank you, Maharaj, for that wonderful introduction. Since this is a talk which is mostly attended by students, even though it's a retirement commemorating the retirement talk for Professor Majumdar, but since most of the audience are students, I thought instead of going technically into one particular area of one particular topic of research too deeply, I would try to give a brief overview of the field of cosmology as I have understood it in the last few years. Especially as a student, one of the biggest difficulties I faced was getting a sense of perspective of how the different things fit together. I mean, if a teacher gives a specific problem, we can always sit and think about it, but how do various things fit together? What exactly is cosmology? So I thought it may be more helpful in the short time that we have to give an overview rather than go too deeply into any one topic. So that is the way I am planning the talk. If you have questions, we don't have a lot of time, so if you have questions, perhaps it will be better if you note it down or keep it in your mind, and after the talk perhaps we could discuss it. And so if there are any questions that you have which I won't be able to answer, fortunately there are at least 3 or 4 people here who are far more experienced than me in the field, so I'll deflect the question to them and hopefully they will answer. So we'll leave it at that. What? That depends on how deep the questions are. So let's see. Okay. So the area of research that I have worked on is early universe cosmology, specifically the field of inflation. So let's just start with a brief introduction from where we stand. So this will be the outline of my talk. So I'll start with just a preview of cosmology. Is the text visible to all of you? The font is a little small and this. Okay. So we'll start with some preview of cosmology. Then we'll go into cosmic inflation, which is the field I've studied more than the others. So little more time on that, and little bit discussion about constraints from observations, and then conclude. Okay, so first we will go to the preview. So we all have heard that the universe is expanding. Of course, there is a natural question. If we want to say the universe is expanding, there should be something that is not expanding, in comparison with which we can say that whatever is expanding. So this was a question I had for a long time. Eventually it got cleared. So the Earth is not expanding. Human beings are not expanding. Solar system is not expanding. Galaxies are not expanding.
I am expanding.
That is in a different, yes.
Which I want to reduce.
Yes. So, but that is in a different sense from the universe's expansion. So any of the gravitationally bound or electromagnetically bound objects that we talk about are not expanding. What is expanding is, so if you take a galaxy cluster, typically that is not expanding, but the distance between clusters or superclusters, that is expanding. So the clusters are moving away from each other. So if you go to a distance scale of about 50 megaparsecs, MPC is megaparsec. So if you go to a distance of about 50 million parsecs, around that scale, things are moving away from each other. So at that scale and beyond that scale, we can say the universe is expanding. Things smaller than that are not expanding, they are staying together. So that's the basic idea. So objects farther than that, as we observe them today, if we look at the light coming from them, we see that the light is redshifted, meaning you know what redshift means, Hubble redshift, but you know the Doppler effect anyway. So redshifting happens. So from that we know that the universe is expanding because farther objects are moving away from us at faster and faster pace as we look farther and farther away. So for an expanding universe, so now that we accepted that the universe is expanding, for an expanding universe, one convenient way of expressing its expansion is through a metric which is called the Friedmann-Lemaitre-Robertson-Walker metric, FLRW metric. I could not write down the metric here for some strange reason, so I won't go into that. But essentially, is everyone familiar with what a metric is? Some of you have not done general relativity yet. So, so if you want to take a distance from one point to another in space, you say the distance is different, delta x squared plus delta y squared plus delta z squared. So the distance squared is basically 1 times delta x squared plus 1 times delta y squared plus 1 times delta z squared. So this, I can write this product as a matrix. I can say delta x, delta y, delta z as a horizontal matrix, and then a square matrix 1 0 0 0 1 0 0 0 1, and then x y z. So that square metric is what I call metric of the space. Now in general relativity, you speak of not just space but space and time together. You speak of space time. So for space time there will be another metric. It will be 4 by 4 because there is time x, y, z. So 4 terms. And that metric looks slightly odd because instead of 1 1 1 1, it's actually minus 1 1 1 1. That minus 1 is for the time coordinate. So for some reasons which you will probably understand as you study general relativity better. So the metric of an expanding universe. So if you take a distance of one space-time point called one event in space-time and another space-time point, that distance will be minus dt square plus dx square plus dy square plus dz square. That's why it is minus 1 1 1 1. That's how the metric looks. Now if you have an expanding universe, so the distance in x, y and z is increasing with time, let us say. So to parameterize the increase in time, we use a scale factor called a of time, a of t. So what a does is a slowly increases with time. So at this time the distance is delta x squared. At a later time the a is not 1, a is something else, so it will be a squared times delta x squared. So the distance has expanded by a factor a times delta x. So the distance squared will be a squared delta x squared. So when you do that, the metric will basically look like minus 1 a squared, a squared, a squared. Because what you want is minus dt squared plus a square dx squared plus a square dy squared plus a square dz squared. So the a comes in everywhere because that's a parameterization of how the space is expanding. So it would have been much easier if I could show it here, but anyway, that is not here. So okay, so essentially the metric, free FLRW metric is a way of showing that the universe expands. So this a, which I will refer to perhaps more times later, is called the scale factor of the universe. So in a simple sense, understand that the universe is a present size, a certain size at right now. Let's say 100 years back, if it was half as big as what it is now, then the scale factor then would be half. Scale factor now is 1, scale factor then would be half, and scale factor even earlier would be even smaller. So that's the basic idea of what the scale factor does. It slowly increases with time. You can set it to be 1 right now, or you can set it to be 1 at some point of time. It will keep increasing monotonically if the universe is expanding. So that's the basic idea. So now general relativity, which some of you have studied probably and some of you haven't. So it requires that the metric should reflect a curvature of space-time. So which is dictated by the matter present in the universe. So basic idea is, if you have if you have matter or energy in the universe, that will curve the space-time. So the basic idea is very simple. So if you have a rubber sheet which is stretched very taut, and if you put a heavy object on the rubber sheet, the sheet will bend over there and it will curve a little bit over there. In a very similar sense, space-time gets curved by any matter that's present in it. The matter can be stars, planets, etc., like Earth, or even us. It can even be energy, like even just photons. They can also create a very, very, very tiny curvature. So any sort of energy can create a curvature of space-time. So effectively, general relativity says that how much the space-time is curved depends on how much matter is there and what nature that matter has. So it's the matter content will determine how the space-time is curved. And expansion of the universe with time is in a form, you can see that that is also a space-time curvature that is changing with time. So that space-time curvature is also determined by what is the matter content in the universe. So bottom line of this slide is, whatever matter is there in the universe will determine how the universe expands. If you understand, if you just take that much, that's enough. You don't need to go into details. Now, if you so we know that whatever matter is in the universe, that will determine how it expands, or if you go back in time, how it contracts. Now, if you look at very far away objects, you are not seeing them as they are right now. You are seeing them as they were at an earlier time. So in fact, I am not seeing you as you are right now, but as you were a few nanoseconds back. And I am seeing the sun as it was 8 minutes back. I am seeing the Andromeda as it was a few thousand years, million years back, and so on. So as you look farther, you are actually looking farther back in time. So if you look at a very distant galaxy, you are seeing it as it was several billion years ago or so. That's the basic idea. So in a sense, when you are looking back, we are looking at the things as they were at an earlier time. So by looking farther and farther and farther, studying objects that are farther and farther away from us, what we are really seeing is a history of the expansion of the universe. We are seeing things as they were at earlier and earlier times. So is everyone clear with this idea? Okay, nobody is shaking their head, so I hope that means everyone followed.
Two kinds of shaking, sir.
Yeah, two types of.
In South India, they nod yes and say no.
Yeah. So anyway, there is no shaking whatsoever here. So let's assume that means a yes. So so we see the history of the universe as we look farther away. So there are certain phenomena that can tell us how far things are. So those are called standard candles, standard rulers, and standard sirens. The idea is very simple. So a standard candle, an example is something like a type 1a supernova. You don't need to know what exactly it is. So it's a certain type of supernova. Now, from physics that we understand, we know how bright such a supernova should be from various properties of the supernova. Now, if we look at the supernova, we see a certain amount of light coming from us. And we know that as things are farther away, the light coming from it will get dimmer and dimmer. So if we look carefully and see that the supernova is exactly so dim, we know how far it should be, because we know how far its original brightness is, how much its original brightness is. So that's a standard candle. You know the brightness of a candle. So by judging how dim it is, you can tell how far it is. So you can exactly get a sense of how far it is. Similarly, a standard ruler is something for which we know its length to begin with. So from seeing how big it appears from where we stand, the parallax, the size of it, you can tell how far away it should be naturally. So everyone, that's fairly straightforward, right? Now standard size, so an example for a standard ruler, okay, that will get complicated, so I won't go into that. For a standard siren, an example is gravity wave signal from rotating from a black hole binary that is collapsing, for instance. So if you take a couple of black holes or neutron stars that are rotating and finally merging into each other, their masses of the two black holes will determine the amplitude of their gravity wave signal. They will create a gravity wave signal first of all. The amplitude of the gravity wave signal and the frequency of the gravity wave signal both are determined by the effective mass of the black holes. So if you look at the signal, a gravity wave signal coming from some source, if you look at the frequency, from that you can find the mass. And once you know the mass, you know what the amplitude should have been when it was emitted from the black holes. And obviously we can measure the amplitude where we are. So by seeing how small the amplitude has become, we can judge how far it should have been so that its amplitude came down so much. So that's the basic idea of a standard siren. So all these are ways in which we can tell the distance of a certain source of information from us, certain sort of source of a signal from us. So we know that the universe is expansion of the universe. It's not just expanding, but it's expanding at an accelerated rate by studying type 1a supernovae and so on. So from that we can see understand what the contents of the universe should be, because as we discussed, contents of the universe determine how they expand. So the contents, as our present understanding, should be about 68% of what is called dark energy, which Professor Abhijit Bandyopadhyay is working on. Then about 27% dark matter, 5% of ordinary matter, which is all the matter that we are familiar with in fact, and radiation which is like light, photons, which is much more smaller, which is basically negligible as of now. Now we also know the nature of these things, so we understand how these different contents will behave as you go back in time. So we know that the dark energy is, the nature of dark energy is such that its energy density does not really decrease with time. As the universe shrinks, its energy density remains the same. It's a very, very strange behavior, which is not very intuitive based on what things we observe in daily life, but that is how it is, and you will probably come across it more and learn it more later. So dark energy becomes irrelevant as you go into the past. Now dark matter and ordinary matter, they behave the same way. How? So if you go back in time, the universe gets smaller. If the volume of the universe is half of what it was, energy density, mass density will become twice of what it is, because total mass is the same. So if you shrink a balloon, the density inside the balloon is twice of what it is. That's all. So that is fine. Radiation does better than that. So it actually, as you shrink the universe, its density becomes even more than twice or 1 over the volume, which for certain reasons, again I would not go into the details. So the observation, so this was a theory of how things change as you go back in time. Now what do we observe? So if you go back, we get a glimpse of the early universe from the far away objects. Now the natural challenge is that far away objects are going to be dim, and the farther and farther we try to look, the harder and harder it is to see anything. So the only things that we see from great distances are the brightest objects with most intense signals that come. So so there are very few extremely far, extremely old objects that are bright enough that we can see. So now, but we do see a few things. So from that, from the little bits of information we get, we try to form a picture of what happened, what is there in the past. But there is a theoretical limit to how far we can see. The thing is, as we go back in time, the universe gets smaller, hotter, denser. So at some point, the universe will be so hot that essentially even hydrogen atoms, forget stars, galaxies, planets and all, even hydrogen atoms cannot stay as one. They actually break up because there is so much kinetic energy in the protons and electrons that they don't stay bound. So the energy of kinetic energy is more than 13.6 electron volts or whatever. So they can't even stay as hydrogen atoms. So at that time, what you have is just hot plasma. So what is the problem with hot plasma? So hot plasma means it is opaque to light. Light cannot pass through plasma. Just like light cannot pass through a glass of milk because it scatters light. Similarly, if you study quantum field theory, you will see that charged objects will scatter light with much higher probability than neutral objects. So if you take a hydrogen atom, if you take a gas of hydrogen, light will mostly pass through it. But if you take a plasma, light cannot pass through it because the protons and electrons will scatter the light. So whatever light we see, whatever light would have existed when the universe was that hot, it cannot propagate very freely. Only when the universe becomes cold enough for hydrogen atoms to form, from that point light is free to travel, propagate to whatever distance it wants. So the farthest object that we can see actually is like a wall of light from the time when the whole universe seemed to have been filled with a hot plasma, like the surface of the sun almost. So that wall of light is called cosmic microwave background. It is not it's not visible light, it's microwave light because it was visible light maybe around the time it was created. But since the universe has expanded, the light has redshifted, its frequency has come down and it's now in the microwave range as of what we see. So basically it looks like this, it's a wall of light. So this is basically, now if you look at the cosmic microwave background, it's coming from all directions. So if you carefully map it, what you are seeing is a photograph of the universe as it was when the universe was very hot. Okay, that was about 13.8 billion, 13.7, 13.8 billion years ago. Right? So this is basically the photograph, but if you look closely at this photograph, you see that it's not exactly the same color everywhere. It's slightly hotter in some places, slightly colder in some places, slightly higher frequency, lower frequency. There is some difference in intensity of light coming from different points. Now this picture is obtained after greatly increasing the contrast. If you normally look at it, it will look exactly like that. But if you very carefully look at the contrast, it will look like this. So some regions are a little cooler, some regions are a little warmer. So the anisotropies, the small differences are like 1 part in a lakh. So very, very small variations. So essentially we cannot see past the cosmic. So okay, before I go into that. So this shows us that in the universe, some places were a little hotter, some places were a little colder. And what that really means is some places were a little denser, more material was present, and some places were a little sparer, as in there was less material there. And after this time, when the universe was a hot plasma, when time evolved and you had hydrogen formed and everything, slowly the places which were denser accumulated more and more matter because they had more gravity, and the places which were sparser lost whatever matter they had, and eventually small structures began to form and larger structures began to form, and essentially you got the all the like large scale structure, galaxies, stars, planets, everything formed from these little variations that you see at the time of CMB. So that's the basic idea. Now what happened before that? So clearly this wall of light is the farthest we can see. We cannot see anything farther than that. But because but our understanding of high energy physics is good enough that we can infer what happened before that. It's not very difficult. Even in our colliders, we achieve energies higher than this. So we know that farther back, the photons became even more energetic. So eventually, so the light particles, the photons would interact with each other and produce electron-positron pairs. And even further back, they would create proton-antiproton pairs. All kinds of pairs of particles were created in the past. So eventually, you will have a universe with a hot soup of all kinds of energetic particles. That's what we would have. And even further back, you would reach a stage where the energy of these photons, energy of all these particles, is even higher than what we can achieve in LHC. Higher than anything that we have achieved in our colliders, experiments, labs, everything. From that point, probably we have to resort more to estimation, guesswork, and so on. We try to come up with models of high energy theory which correctly fit things. So probably this is more into Professor Sanjay Bishwa's area of research. So anyway, so that's at higher scales than in LHC. Now eventually we reach Planck scale energies beyond which there's a Big Bang singularity. So at that scale we can't say much about it. So this is the starting scale of the conventional Big Bang theory. Now, now I'm going to come to cosmic inflation, which I did not even mention till now. What is cosmic inflation? So from the time of Big Bang to the time of this recombination. Recombination is the time when hydrogen atoms were formed, the time when this light came, the CMB, cosmic microwave background. So from the Big Bang to the time when hydrogen atoms were able to form, which is recombination, the time that it takes is fairly easy to calculate. It's around 4 lakh years, 380,000 years. Now, in that time, it is not possible for light to travel from one end to other. So if you see this picture, so if you take the left extreme, let's say here to here, even if you travel at the speed of light, in 4 lakh years, you cannot go from there to there. The universe is that big. So how is it that that point and that point got the same temperature? How is it that they somehow knew each other's temperature and came into a thermal equilibrium? So that's one question you could ask. So why is the CMB so uniform? Why is the temperature the same everywhere? Now another question is, from our study observation, we know that the universe should have been flat, spatially flat at that time. Not space-time, but spatially it was flat at that time. Now, if this universe had to be spatially flat at that time, it should have started out even more flat. So why did the universe start out so extremely flat? Why couldn't it have been more curved and so on? So that's called the flatness problem. It's a fine-tuning problem, sort of. And then you could also ask, early Big Bang times, there could have been many exotic things like monopoles, magnetic monopoles and things like that. If they were there, we should see them now also, at least once in a while. Why is it that we don't see any magnetic monopoles? Why are they so rare? So again, we don't know why these things were not there. So one possible solution is if the universe expanded very, very quickly for a very short period of time, then whatever monopoles you had would be distributed so sparsely that you can't see anymore. I mean, they are so rare. And whatever curvature universe had in the beginning would have been stretched out so much that it looks very flat. And whatever points we see as very far apart at CMB, they were initially so close and they were stretched apart by this very fast expansion. So the expansion is the reason why everything looks so uniform, because the vast universe that we see in CMB actually came from a very small patch in the beginning. It was just a very short period of very quick stretching that made it appear so big. That's a basic line of reasoning. So that is called inflation. This is a field theoretic part of inflation. Probably you don't need to pay much attention to it. So the standard way of getting inflation, a sudden expansion of the universe, is through is a simple way of doing it is through a method called single field slow roll inflation. So if your universe, most of the energy in the universe was comprised of the potential energy of a single scalar field in quantum field theory. So that can lead to conditions that appear like inflation, exponentially fast expansion. So it requires some study of field theory. So probably most of you may not be familiar with that kind of thing. Now after inflation, so there is an inflecton field whose value will slowly change from over this range, and eventually when it reaches this ditch and it falls down here, then that slow roll ends, inflation ends, and then the energy in this, so you see that the potential energy is very large over here, but when it reaches this bottom, naturally potential energy is gone, so that gets converted to kinetic energy, and that gets transmitted into various other fields and electrons and protons and everything eventually. That's the basic idea. So whatever energy was in the inflaton eventually gets transmitted to other fields. So this is the kinetic energy, this is the potential energy. Anyway, so okay, this slide is probably even less clear. It does not matter to understanding this too much, but the basic idea is, so if you look at such a theory quantum mechanically, so you cannot avoid fluctuation. So quantum mechanics says that the G here is basically the metric which comes in general relativity. Now the metric can have small fluctuations, and similarly the phi is the field, and the field also, its value doesn't have to be exactly uniform everywhere, it can have small fluctuations. So as long as quantum mechanics is involved, you cannot avoid fluctuations. So you have to find some way to parameterize fluctuations, and there are two different types of fluctuations that you can talk about, the scalar fluctuations and the tensor fluctuations. I wouldn't go into detail too much, but essentially scalar fluctuations can be thought of as fluctuations in density. So if you say a little more energy is here and little less energy is here, that's a result of something like a scalar fluctuation. And tensor fluctuation is connected to what we call a gravity wave. So tensor, so you remember when I talked about the metric. So I said the metric is basically a matrix, 1 0 0 0 1 0 0 0 1 and so on. Now when you have a matrix, different terms in a matrix can change, can have fluctuations. So in addition to, so these different fluctuations of the different terms in the metric can change in a harmonious way, coordinated way among each other. So basically they have changed like a matrix does rather than like a number doing. So basically, okay, so if you take fluctuations that are vector fluctuations, what that really means is a vector that looks like this changes into a vector that looks like that. So the change in the x coordinate and the change in y coordinate and change in z coordinate are not completely independent of each other. They sort of change in such a way that the overall length of the vector remains the same. So similarly, a tensor fluctuation is one where the different components all change, but they don't change independently. There is a coordinated way in which they change. So such tensor fluctuations are eventually what we call gravity waves too. So which is the thing that we recently observed in LIGO. Those gravity waves were not created by inflation, but inflation could also create such gravity. So anyway, inflation predicts that there will be density fluctuations and there will be tensor fluctuations. And depending on the theory of inflation, the strength of these fluctuations and their various features will be different. So one great success of inflation. Now inflation till now was a possible explanation that explained why the universe was so flat and so uniform and all these things. Now one prediction that that inflation made was that very naturally it would give you a scale invariant fluctuation. Scale invariant means the fluctuation is same at different length scales, and if you wait for long enough with gravity collapse and everything, the fluctuations would look something like this. So the red dots here are observational data, and the green line here is what inflation predicts. So when we studied the cosmic microwave background, you remember this picture was obtained by carefully studying the cosmic microwave background. So you can see there are small fluctuations. So when you carefully study these fluctuations and analyze and do a statistical analysis of that, you eventually get basically how strongly the fluctuation is at each length scale and so on, and you plot the power spectrum. It looks like, it would look like these red points over here, and you can see these red points neatly lie on the green line, which inflation can easily predict. So it shows that inflation can in a natural way predict the kind of power spectrum we see in the cosmic microwave background. So that's like a very good indication that inflation may have been something that actually happened in the past universe. So I'm actually quite far in time, so maybe I should try to wrap up in 5 minutes, I guess, right? So I'll quickly go over. So after inflation, what happened? So we had a lot of energy in the inflaton field which got transmitted into other fields, and eventually you got a lot of highly energetic particles, standard model particles, and possibly dark matter particles also, depending on the nature of dark matter. And eventually, so when you had particles, so we normally expect a lot of particles and antiparticles, but in the present universe we see only particles. So in the past we expect there to have been roughly 10 billion particles and antiparticles compared to every particle that we see now. So what that really means is we had a huge number of particles and antiparticles, but there was a 1 part in 10 billion difference between these two numbers. So the remaining, all of it almost perfectly cancelled, and that remaining small 1 part in 10 billion is what is remaining today. That is all our stars, galaxies, everything that we see. For some reason, there is a slight asymmetry between the number of particles and antiparticles, and that asymmetry is the reason why we have particles in the present universe. So baryogenesis is a way in which we could try to come up with a explanation for why that asymmetry came in the first place. And eventually we had protons, electrons, neutrinos, photons, and so on. And at some point, the protons and neutrons basically combined to produce helium and deuterium nuclei. And at a later time, even from the nuclei, atoms were created, hydrogen atoms and so on were formed. That is recombination. That is the time when CMB formed. So all these things happened before CMB, but they are fairly straightforward to understand. And then eventually, after CMB was formed, there was a long period where there was no source of light in the universe. So whatever photons were there in the beginning were traveling, but there was no source of light. The universe was kind of dark. It's called the dark ages. And then what happened was the places with a little more gravitational stuff started collapsing more, and when they collapsed, they slowly, stars and things like that started forming. And once a star is formed, you know, there is a lot of heat produced and photon pressure, and so fusion happens and light begins to be produced. So then the universe re-ionized at that stage, and so various things. So after that, structure formation, then later on acceleration of the universe and so on. So this is basically a brief history of how the universe proceeded. You have inflation in the beginning, and that is not explained well, but here is the cosmic microwave background time, and after some time you had a dark age from then, and at some stage you had the first stars formation, and from then on there is more of structure formation. And you can see the background of the boundary of this thing. So it was initially curved like this, and then finally it started opening up again. That's an indication that the expansion of the universe was decelerating for a while, but slowly this dark energy that we talk about, the strange thing, became more and more important. So it started accelerating again. So it started opening out. So it started expanding like this, and then it started opening out. That is the reason for the thing curving outwards in the end. It's a very small difference, so I don't know if it's easy to see from where you're sitting. Anyway, so now the universe is accelerating as far as we can see. So just constraints from observations. So our eyes and ears, basically we study the cosmic microwave background. That tells us a great deal about what happened before it. Then if we study things like 21 centimeter line and Lyman alpha forest and so on, that tells us a little more about what happened during the dark ages, that is just after the CMB period. And there are efforts to come up with experiments, telescopes, measuring apparatuses to observe these things better. And then there is large scale structure. So after structure started forming, galaxy clusters, galaxies, all that started forming, naturally we want to study how that works, we want to map the structures very carefully and see how they evolved and so on, and whether it agrees with our understanding of gravity. So that is large scale structure probing. And then of course gravity waves can have implications about a variety of things at various stages of evolution. So the cosmic microwave background observations started, you had COBE, then WMAP, then Planck. So there is greater and greater resolution in studying it carefully. So COBE was very blurred, WMAP more clear, and Planck was much more clear. So that's how things get better. Our observation power gets better with time. So there are some disappointments also, like a few years back, one particular experiment called BICEP, they stated that they observed a certain form of polarization of the cosmic microwave background light. So certain patterns in polarization, like these spiral patterns that you may see here. So that was called B mode polarization. It was important because that could have explained gravity waves produced during inflation, which will be a great prediction of inflation. But the problem was that eventually it was found out that between us and the the cosmic microwave background, there is a lot of galactic dust, polarized dust in galaxies. And the uncertainties in how much of polarized dust there was and how much they were polarized, that could explain the same kind of signals. And therefore, the BICEP analysis did not fully account for those uncertainties, and therefore the signal observed by BICEP may not have been CMB polarization, it may have been some signal created by dust. So dust basically explains whatever you saw, it is not a CMB polarization, so you don't know, you have nothing, you have no new result. So when it came, it was very exciting because that could have said a lot about inflation, but eventually it was shown that on careful analysis, that signal is nothing much. So then basically the excitement went away and That's sort of disappointing for the field. So there is a great deal of careful precision observations to be done in these fields, and that is being done right now. And on the other hand, there is no scope for error. You have to be extremely precise also. The slightest mistake can, it's basically invalidates your data. So that's the basic idea. Anyway, so there are other probes like dark matter probes. You try to see how much of dark matter is there. Dark matter is more relevant at later times, but it's also relevant depending on how dark matter may have been involved in the inflation process itself, or some of the early stages of evolution. So there are various kinds of dark matter probes. Again, I won't go into detail in that. That again, maybe Professor Sanjay Biswas at some stage might discuss. And there are various types of dark matter. And the promise of gravity waves. So gravity waves are basically metric perturbations. As I said, the metric itself is perturbed, and that propagates with the speed of light, as far as we know. So it's usually produced by violent events. Inflation is one example. Bubble collisions is another example. I never said what bubble collisions are. It may not have happened also, but if necessary, we can probe into that more later. And it can also be created by the one source which I've actually seen, which is binaries of black holes and neutron stars. So these are very heavy objects and also very compact. So when you have a very heavy object, it curves the space-time quite a bit. But if it's also very small, then just outside its boundary, the space-time is extremely curved. And if you have two very heavy and very compact objects quickly rotating and finally collapsing into each other, then in the vicinity of these two objects, there is a huge variation in the metric of the space-time. It's curved to a great extent. And this process is so violent that there is a lot of metric curvature variation that is produced. And like ripples, it is basically propagates out in space in various directions. So that is what experiments like LIGO observe, and how they observe is another story in itself. It's an extremely precise observation, and I won't go into detail in that. So these things can produce gravity waves, and gravity, we have already seen some mergers, and there is one particular merger called GW 170817, which is 2017 August 17th. So that particular merger is particularly interesting because in addition to the gravity wave signal, we had some other signals also coming from it, like visible signal and so on, neutrinos also, I think. So there is a huge amount of information that can be gained by studying gravity waves. So it's really, in a sense, a hot topic in cosmology and astronomy going forward. So there is a lot that we can tell from gravity waves. So to conclude, so basically the moral of the story, cosmology is very closely connected to various areas like field theory, particle physics, astronomy, and so on. There is a close interplay of theory and experiment. It's basically a data-driven field. So if there is a certain aspect of cosmology where data is likely to come, usually there is going to be more funds there, more jobs there, more interest there, better chances of publishing interesting papers there. So usually people try to move towards such areas, specific questions which can be answered by observations, by new telescopes and so on. And the downside is, of course, that we would never really exactly know what happened in the early universe, most probably, but we can aim for a better understanding. And eventually the field is driven by data. The downside is if the data don't show anything interesting, like the bicep data was killed because it was not observationally exact. So then that can also make the field at some stage less interesting if there is no hope for better data. So that's a natural thing that might come. I'll just end with a quote by Einstein. The most beautiful thing that we can experience is the mysterious. It is a source of all true art and true science, and perhaps you could say true spirituality also. And he to whom this emotion is a stranger, who can no longer pause to wonder and stand wrapped in awe, is as good as dead. His eyes are closed. So thank you for patiently listening. Probably we don't have a lot of time for questions, so let's. Is there any quick? Yes. Thank you. Yes. Yes, A will depend only on time. The way we parameter, we assume it's spatially homogeneous and so on.
So different portions in the universe,
Yeah.
similar.
We parameterize in the, yeah, we say that.
Why is it so?
It's basically what we observe. We see that it's pretty consistent with the whole universe expanding more or less the same way. So it's convenient to take a scale factor as just a time dependent. So that's basically it. Yeah. You could of course consider alternatives of all these things. So sometimes they make the theory much more complicated, harder to analyze without any actual gain in explaining observations better. So you don't. Any other questions? Okay, thank you very much. Let's just go for the